So in this video we're going to look at another slight complication, which is where the drug, rather than existing just in one compartment, rather than thinking about the body water as just being a single compartment, this time we look at the situation where we have two possible compartments. So if we think about, we have our original compartment, which is what you might think of as the main sort of body water, if you like. But that is connected to another compartment. So the first one might represent the blood, plasma, and maybe body water. And this second one represents the tissues or fat. So you can get exchange between the compartments. However, and this removal from the blood would be the processes of elimination, but the movement of the drug into the tissues represents redistribution. So the redistribution phase is given by that little bridge, the arrow on the bridge connecting the two compartments. So if you think about your concentration versus time graph, we'll just sketch one out. You start with a certain concentration. The drug goes straight into the plasma, into the blood, and it distributes everywhere into that. So we're still assuming rapid distribution in the central compartment, or what you might call the plasma. So that it goes straight into the plasma, but then from the plasma, the concentration in the plasma, so Cp is the concentration in the plasma, the concentration in the plasma falls quickly and then falls more slowly. And this initial phase is actually redistribution. So it's leaving the plasma, but it's not leaving the body. So it's being redistributed into this other compartment. Whereas the longer, what you might call the terminal phase, is where it actually leaves the body. Now that graph doesn't look too different to what we saw before. By eye it's very difficult to see that difference, and that's where a log plot is really important. So let's do ln C versus T, and what happens is you don't get a straight line log plot. So you start off with something that might look like that, and then you get a straight line. So this here is the terminal phase. So where you see it's a straight line, so a straight line log plot, a straight line log plot tells you that it's behaving as a single compartment. In the first phase, it's behaving as two compartments, and you've got redistribution occurring between the two compartments. So generally what we would do to calculate the area under the curve in this instance is, if we want to know the area under the curve here, so if we call this T1, this is T1, and that's the corresponding C1, just to give it a name. The area under the curve, let me just change colour. The area under the curve here is now C1 over Kz, and Kz is the terminal phase rate constant for elimination. So the terminal phase version of the Ke. So you can work out the Kz from the gradient of this log plot line, where it becomes straight, and then you can use that to work out the area under the curve for this terminal phase. Then to work out the area under the curve for the rest of it, you need to use some sort of estimation process, such as trapezium rule or counting squares. Okay, so this is just another extension. The simplest case is a single compartment model. Then we've had two more complex cases. One is a two compartment model, as we've seen here, and the other is zero order elimination, as we saw in the earlier video. It is possible that you can get zero order elimination with two compartment model. That makes it significantly more complicated.